my blues is one of those professorial blues situations because, the basic idea is deep, it's beautiful, it's wonderful. Everybody should know it. And, no matter how I get started to explain it, we get lost in the woods. So maybe this picture helps. The way I see dynamical world, very coarsely is that there is a world of order. There are things that are as simple as that. No matter what you do, your emotions slow down, die down, you stop. If there's something like energy conservation, you're not allowed to stop, so maybe you oscillate, but it's a very orderly thing. Could be just oscillation, quasi-oscillations, etc. In the last 20, 30 years, physicists have also had to grapple with the opposite, as far as possible distant part of the laws of nature, which we now call chaos. It's not a chaos in a human sense because we bring lots of order by bringing theory into analysis. Ergodic theory, symbolic dynamics, many tools make this chaos not so chaotic. But these situations where, no matter how you start, your neighbors run away, other things return, you return into the same regions. In other words, you're in a world of positive Lyapunov, everybody runs away, and positive entropy. There are very many ways of bouncing back to where you are. And once you get a hang of it, especially in examples that are working out, it's quite clean. It requires some more mental effort than oscillatory motions that we learned first, but it's pretty clean. It's like shuffling cards or something. It's, it can be explained. And then in between live dragons. In between, there are all kinds of things. We know this from numerical studies and from particular excursion into the world between the order and the chaos. There live complicated combinations of chaotic and orderly motions. There are all kinds of things going on. And one very natural question you would like to ask is, what's the border of order? Can I define that? How do I know I'm out of orderly world entering disorderly, chaotic one? That's what renormalization theory is about in statistical physics, in thermodynamics, in theory of phase transitions, and also now in theory of dynamical systems. The idea of renormalization is that as you approach the border of order, you kind of slow down because you're not sure whether you're supposed to be orderly or disorderly. And then there is, precipitous edge between the two, very loosely speaking. And to see it, you have to use the lens, which is called renormalization theory. You have to blow up the region, and you have to keep doing it over and over again, constantly probing whether you belong to order or you belong to chaos. Now, in dynamical systems, this turned out to be much harder than one thought for centuries. The border of order is what we today call fractal. It has very complicated structure in many dimensions. And the more you blow it up, the richer and more complicated it gets to be. And then in this world of, great complication, this little miraculous thing happened that we are teaching you in the two lectures, which is called universality in, let's say, renormalization, or universality in period doubling. Once you learn one of these universalities, there are very many examples you can work out. many have been worked out. It just so happens that, and it's in the nature both of experimentation, numerical and with nature, that one tends to run into the most robust version. So it turns out, there are infinitely many normalization situations, schemes where you can actually get to the border in a very precise way. Period doubling happens to be the most robust one. So that's what you see most often in experiments. So that's what we're trying to get across. But by the time I start doing it, it looks much more complicated than in some, deep sense it is. It's just that in the order, you don't have to be very careful because everybody just oscillates. In chaos, you don't have to be terribly careful because everybody runs away exponentially fast and they come back, and you don't need lenses to describe this kind of behavior. But in situation where you cannot decide whether you're on one side or the other, then you need some special tools. And the basic idea is, because you slow down, you have to redefine your time. So in period doubling, successive stable solutions of limit cycles of one-dimensional parabola or one-dimensional unimodal map, their length grows exponentially. So, to see the next, if I've seen a 4 cycle, I have to wait 8 original units to see the 8th cycle and 16 to see the next one. So the time is not very useful. So you have to, rescale it. You're really logarithm of the time is really the time as you're approaching the border. So that's one of the things you have to do in normalization. And the other one is you get finer and finer detail of who is here and who is there. So you have to have space or state space blow up normalization, and that's what this lens means. Okay, so back to our one example that we are familiar with. The first example and the simplest. And, I love this thing in some way. I feel a little bit unsure whether I should teach you this thing because I'm not sure that you will actually have to renormalize in your life as a biologist or whatever you come to do next. I hope I'm not wasting your time. But the steps are very typical of things that you have to do studying dynamical systems. So in that sense, it's not a waste of time. What do you have to do? Always. You have to find fixed points. So first thing you have to do is you have to get used to the idea that when you have chaos, when you have these 1- and 2-dimensional examples we studied, these limit cycles, it was typically just one limit cycle and that was it. When you have a chaos, you have infinity exact solutions and you can make it more precise. Typically, as you look at the longer and longer period solutions, their number grows exponentially with the length. You can't beat exponentials unless you have some good ideas. Let's think about just period 2 solutions. We know how to do fixed points. Period 2 means that if you apply your law, your map, your iteration to previous point, you get to the second point. If you apply it to iteration of the first point, you have to apply the function twice. And the period 2 means that you come back. So that's what we mean by period 2. So now you can try to do this analytically in these silly examples we do in the course. Everything is very simple. So typical, simplest possible nonlinear example of dynamics is a logistic map, which is, has 0 at the origin and is second order. And this notation here, composition of maps or iteration, that means f of x. So start with x, get a result, and then apply the same function on the result. In dynamics, one tends to write f to the n, where n is not a power. You're not raising this number that's the function of x to power n, but you mean you keep repeating these iterations. So you take a function of a result of a function, same function of result, applying it on an initial point n times. What it means is that, I see x here, xn plus 1, I should replace it by the function, which is rxn 1 minus xn. So this is xn replaced by its predecessor. Then this has to be also replaced. So you multiply this by 1 minus the same formula. And you pretty quickly realize this is a horrible thing, because as I multiply these guys, the highest term on the right-hand side is x squared, it has x squared. So I pick up term that's of size x4. So I find out that, xn plus 2 there's a constant term sometimes. In this case, it's 0, but so then you get this term. With some constant you have to figure out for a particular map. Then you get square term. Then you get cube term. Then you get quartic term. So you start with this innocent parabola, you get some complicated mess just going 2 steps forward in time. If you do it for 3 steps forward in time, you'll realize this will go to the order 8. So this is not much fun. Even the simplest thing, which is a 2-cycle, is quartic. It's possible to be clever and do some stuff analytically, but sooner or later your luck will run out. You won't be able to do this. So what's a wise thing to do? What has worked for us before, so let's try it again. Let's draw pictures. So what does this thing look like? We'll draw it just on unit interval. 1 is kind of a natural scale in this problem. Whenever I'm looking at the map, I'm interested in fixed points. They always sit on a diagonal. But this is designed that if x goes to 1/2 minus x, this survives. So there's a symmetry in this problem, so you can tell that left and right branch will be similar under reflection over 1/2. So that's always something. And, it's quartic. So what can the quartic do? So I'll conveniently write an example very clear. Quartic can have maybe only 1 crossing of diagonal, but at most it can have 4 of them, because, quartic is a function that goes up, goes down. It has this 3 laps of down, up, down again. So at most you can get 4 things that are fixed points. Now you realize that 2 of them you already know, because you knew this fixed point already. And when you think about it a little bit, this guy, which came just from looking at this other 0 over here, this guy, when you go through bifurcation, is still there, it just survives. So you know this is a repeat of a fixed point of first iterate, it just map itself. But now quartic has 2 more solutions. So you have to find those. Now that's not so difficult still, because you have a polynomial. You know that you can write polynomial as a product of x minus root over all roots. You know two of them, so you know that you can divide this quartic polynomial, the polynomial of second order, and result is a quartic one. So you know you can divide it by the roots that you already have. One is 0 and the other one is minus 1/2 plus 1r, this guy here. So you divide by them. So you have 4 periodic points. And you can reduce this computation to quadratic computation. And you know how to take square roots. So it turns out everybody will be able to give you, sooner or later, write analytic formula for all the roots of this second order polynomial. And, it looks something like this. When I look at this map, there is a left half and a right half, there is a bump on it. So if the root is on the left side, I'll call it left. If it's on the right, I'll call it right. So there are periodic points that I can label by the fact they hop from left and right, or start on right and hop on the left. So there are two of these periodic points. And the root turns out to be, some stupid algebra. But you learned something already from this. It turns out, R should be at least as big as 3 for this root to be root of a positive number. If R is smaller than 3, then you only have one new root. It's not very exciting. So we already know something about this map. We should really look at the interval larger than 3 and smaller than 4, because at 4, I start mapping outside of unit interval, and that's not nice. So you can think of this period 2 that we found graphically here, analytically here. You can think of it in the original space. And what happens in the original space, the web diagram, cobweb diagram for it, says, if I start on the right-hand side, in next iteration, I'll end up on the left-hand side. If I start here in one iteration, I'll end up on the right-hand side. And if I iterate 2 times, I'll come back. So that's one way to understand the dynamics of it without suffering analytic things. That one turns out to be not terribly useful when you look at longer cycle, because you just get a very confusing picture with lots of cycles running left, right, right, left, etc. It's really hard to keep track of. But the main property is that in 2 cycle, left, right gets mapped into right, left in 1 step. Now, more useful thing always is to look at the iterates. Because the nice thing about the iterates is that when you look at that iterate, you convert every problem into a problem of fixed points, and you know how to find fixed points. This also helps you understand bifurcations. For example, if this map just happens to be such that when it dips down, it's tangent to the diagonal but doesn't cross it, you get one of those things you already know, that on one side you have stability, on the other side you have instability. This is unstable. This is unstable. This is, half stable. So these pictures of looking hard integrals help you with bifurcations as well. Basically, my feeling is we can do this as exercise in this book, but in real life, this analytic stuff won't be useful. That's the nature of nonlinear problems. There are infinitely many of them. each one is ugly. Period doubling is one very cute way of out of this dilemma. Start this logistic map. If I take in one dimension some value of x and unit interval, logistic map is a thing that maps it into unit interval again. So map looks something like that for some value of r. This is 0 to 1. This is mid-interval. The mid-interval map has a zero slope. It's a very special point called critical point, xc. It's designed always to have one fixed point, but the other one it has for r larger than 1/3, as we already saw. So that's one example which is very useful to get intuition about chaotic iterations in one dimension. This is all old stuff. So this was introduced by a great French mathematician called Julia, I think 1910 or something like that. And there was another great French mathematician, almost as great as Julia, whose name is Fatou, who found this an ugly form of looking at parabola, so he prefers to forget about linear term. It's just a coordinate change, nothing interesting happening. It says, let me center it so that in this case, where x is 0, I get the maximum, and maximum is this parameter, and I vary it. What do you do with this thing? So the first thing that almost anybody tends to do is to look at a time series. Time series at the beginning looks like a sensible thing. This is time. Time is in integers. We'll look at state at time 0, 1, 2, 3, and on. So this goes on forever on the right-hand side. We are looking at the value of what I would call field value of my dynamical variable at time t. For example, if you take sufficiently small r, so this fixed point has a slope that's smaller than 1, then you will find that no matter where you start, you'll bounce around a little bit, but because it has slopes smaller than 1, its neighborhood shrinks at every iteration. And if you write yourself a little help curve here, you'll find out that dynamics is going to a constant, and then you just cut it off this picture. Then, in the way that we discovered in experiments I tried to explain last time, as you increase this height parameter, you find an attractive period too, but it's something that if you squint correctly, you will understand that this is period 4. Very soon, it's very hard to squint and see it. If your R happens to be, again, this has this property of this map, no general interest, you will find period 8. And now you really have to squint to see this thing. So sooner or later you realize this is not a good way to visualize what's going on. The real visualization, the next attempt will be to do it in what we call state space otherwise. So both axes are the field and not one is time and one is the field. So let's look at this a little bit more carefully again. Remember, map was a parabola like this whose height was controlled by parameter r. If you take the mid-interval, then this is 1/2, this is 1/2. So the height of the mountain is r over 4. So that's very precise. First thing you notice that if r is too small, so if it's smaller than 1, there will be very boring dynamics, which is origin is attractive, and no matter where you start, you just end up tuk, 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 tuk in the origin. So you always have this fixed point. That one will be always there. I'll call it the left fixed point, 0. If you make the height a little bit bigger, this parabola will finally get a slope larger, and you can see what the slope is. Its value of r for small x here. So it just has to be larger than 1. You'll get something that crosses the diagonal. There's another. This is unstable, not stable anymore. So this has to be stable at the other end. Something has to happen there. This fixed point, when it exists, has a property that I can remove one fixed point by dividing both sides by x0. So I have a condition 1 equals r, 1 minus x star is condition for this fixed point, so that's easy. I divide both sides by r, put 1 on the other side, so that's the location of the next guy. And so that means that, interesting r has to be larger than 1. Next thing that we're always supposed to understand is stability of our solutions, our fixed points. In case of one-dimensional maps, stability is very easy to understand because it's simply given by chain rule. So suppose I'm looking at the n steps forward in future. So I start at x0, and I'm looking at stability of nth iterate that I obtain by taking derivative. It's a matrix of velocity gradients, but it's one dimension, so it's 1 by 1 matrix. That's the only element. I can write this as an iterate up to preceding by the last step, penultimate step. And now I can use chain rule. I take derivative of this and I evaluate the function at x equals x n minus 1. And then I have to take derivative of the rest by the chain rule, df n minus 1, dx x, starting at 0. But I notice this has the same form as the original function, just one less step. So I can write this as a product by iterating the chain rule as derivative with respect to the variable, not for the point, but last all the way to the original initial point. So in one dimension, stability is incredibly simple. If I know the trajectory, if I know what points exist on it, the stability of a trajectory is simply the product of derivatives at each point. This is one slope, this is another slope, and if I have periodic point, I'll just multiply these by derivatives together, a very simple formula. In this case, I have also a very clean definition of Lyapunov exponent. When we defined it originally, it had to do with the dominant eigenvector, eigendirection of a d by d matrix, but now we have a one-dimensional matrix, and Lyapunov exponent is rate per unit time. So to get rate per unit time, I have to take a logarithm of this stuff. And to get rate per unit time, this is integer time, I have to divide this by number of steps, which is 1 over n. Logarithm of product this is a product, is the sum of derivatives evaluated at each step. But this is really cute. So it says that stability, or Lyapunov exponent, is an average stretching, because when you have n steps of a trajectory, you measure logarithm of its stretching at n step. You measure it over all the steps. You divide by n. So it's an expectation value of logarithm of phi. Now, this should be the simplest thing in the world, because you started as a parabola, right? So derivative is linear. It's actually 2 times r phi x. You know what the derivative is, because your original formula was this. So you know that each one of those guys is simply 2 times, quadratic term, from quadratic terms plus, the linear term. So you know what it is at every step. And you just iterate in this map. Your calculator is producing next number. What could be the problem? Well, try it for a parabola, the simplest nonlinear system. It's very educational. It turns out that it's really wild as a function of this parameter. If you evaluate it for different stretching parameters R, it goes to 0, it goes to positive number, it's well behaved for some short interval, then it jumps and does something else. So plot is an interesting experience if you do it. I recommend it. The other thing in this system, we already noticed that here, generally, if I start at a random point, there'll be transients. So I have to wait for transients to die before I start believing the average that I'm computing. And, it's not easy to convince yourself convergence. Sometimes it's slow, etc. So it's very easy to write Lyapunov exponent, especially in 1 dimension. It's quite hard to do something about it. But here's a nice thing about stability. Suppose you made this a little bit lower in such a way that this fixed point and the critical point, meaning the maximum of your parabola unimodal map, are the same point. The slope of critical point is 0, right? On this side, it's positive. This side is negative. As you approach it, it gets more magnitude. And on the critical point itself, it's 0. So in 1-dimensional maps, that doesn't happen in higher dimensions. We have something that's called superstability. And that has a weird property that once you're there, your convergence is infinite. Your transient immediately falls into the super stable solution. What's going on is when you look at your formula for stability, it's a product of terms. And if any one of them is critical, if any one of them in your trajectory has gone exactly through this point that doesn't know where it's left or right, it's perched in between, this product has to vanish, because one term in the product is vanished. So this is true if any fx n equals 0. And if you have a periodic orbit, this is running over all points on period. So every periodic point in a periodic orbit will have same stability because of that formula. And that means that if one of them is super stable, all of them are. The picture might be something like that. Let me just kind of sketch what a period 3 might look like. So there could be something that goes like that. And then comes back again. So, it has a point x0, which gets mapped into x1. which is same as x critical, and this gets mapped into, I'm not doing this very well, but into x2, and then x2 gets mapped into original thing. So it turns out that when you have a periodic orbit, you might be able, by changing the parameter, find nearby superstable periodic orbit, which has a property that its stability is 0. So any error you make in one iteration, it's crunched to 0, because this multiplies the errors you're making. So you are super stable. You just can't make errors if critical point is included. That makes calculations, your pocket calculator, work very nice, because you don't have to worry about converging to the correct answer. I will try to use this map, but Paul map, the one that looks a little bit simpler, rather than this one, to one more time motivate my big song about border of order and renormalization. So let's do these calculations for a function f of x r is a constant minus x squared. In other words, it's something that, depending on what r is, if r is too small, I get, but big enough so this is unstable, I get something here which is stable, but to the left of critical point, which for this map is at x equals 0. So this is what happens if I have parameter value smaller than the critical one, which Strogatz calls R0. Then there is one very special value where my fixed point equals critical point. And when you look at this value, the slope of this map, which is the first derivative of the map, so the slope of this map, the one that goes into stability, is minus 2x. I want to be super stable. So that means x equals 0. And I want this to be a fixed point, 0, 0, r. So r0 happens to be in this representation very nicely at the origin. And if I am at r larger than r0, what I have is a fixed point here, which is not supercritical, and its slope can be smaller than 1 in magnitude, in which case it's attractive, or larger than 1, in which case it's not attractive. The situation for a fixed point, there are 2 of them, and that was the solution if I wanted to get a super stable one. Now let's check out 2-cycle. If I have orbit of period 2, then 2 steps forward in time, it's a fixed point. I'll need a different parameter value, call it r equals 1. I would like to find a superstable orbit of period 2. So I'd like to have ddx, because those are easiest to work with. And if I can get one, let's get one. By chain rule, that's product evaluated at the image of the fixed point. That should be 0 to be supercritical. No, super stable. And I have the analytic formula for it, so it's minus 2x1 minus 2x2. And that can only be 0 if one of these guys is 0, and that's obviously the one in the middle. So let's call that x equals 1. Then when I put that into my formula for the second iterate, second iterate should be fixed point. That's a fixed point of second iterate, or periodic point of period 2. So now when I put that one iteration, second iteration, I get R1, R1. That's what the parameter value should satisfy. So I have a superstable period 2, which means that R1 should be 1. I remind you, I'm doing a 2-cycle. So now, convenient way to think about this is to actually plot the 2-cycle. And you've already seen what that function looks like. That function, has a wiggle. Then it crosses diagonal, hangs with the old fixed point, but there is a new periodic point and crosses diagonal again. It looks something like that. So you get a 2-cycle plus the old guys. And it has a property which, I didn't draw very well, but it's actually, this fixed point has to be on 0 because it needs to be super stable. So I need to include this periodic point here. So that's X critical as well. Also, this is a blues day because the idea is beautiful, but my explanation is just boring you to death. Now, one makes an observation that could have been totally misleading, wrong. Nobody says this should have worked out. And the observation is that if I think of renormalization, as I told you in the beginning, that there should be a magnifying lens, which enables us to look at small details close to the border of order. Then you notice that a superstable cycle has two of these periodic points. Both have to be at the tips, at the critical points, because they have to be superstable. And they have fixed points, so the first derivative has to go through, be horizontal and come back down again. So their slopes are horizontal here. They're superstable. And then you say, well, look, if I look at this little window, which is small because this bump is smaller than what I have here, and I look at this window, they both kind of look as what I started with. I started with this thing, but this guy is upside down. And this guy is not upside down, but he's a little bit to the end. So let's focus on the central part and say, if I clip it out with my scissors, so I take X and this thing, is upside down, so there's a negative slope. But if I change the scale unit, so it used to, I was measuring everybody from 0 to 1. Let's measure it in new units where alpha, I will tell you something that you couldn't possibly know when you got started to it. It'll turn out that this alpha is of order, 10 over 4, roughly speaking. So that makes, I have to go smaller distance in here to run over unity here. So I've rescaled my X. And then this guy is the height 1, because I showed that this fixed point had R had to be 1 for this fixed point. So I translated some amount. You're totally allowed to change coordinates whenever you have your dynamical systems and mappings. That's just what it says. Change a coordinate doesn't change the thing. And this thing gets blown up to look like what we had before, but by translation, I've put the fixed point down at the origin, and then I multiply by some number, which will turn out to be minus 2.5, roughly speaking. And if I do that, I will get the width of this little window to be from 0 to 1, well, from minus 1/2 to 1/2, if you wish. And now, because it's negative, x and minus x will interchange. It's symmetric in here, but its square is not symmetric because it's positive, so you have to multiply by this number. And then you say, voila, if I'm not looking very carefully, this is the same map. The only difference is that when I look a little bit more carefully, this map is computed for our different parameter value. We can write this as a formula that says fx r0 looks like the second iterate for a different parameter value, r1, with the spatial structure blown up by this factor alpha. And I'm looking at a second iteration to extract this. So the map has to be iterated twice. And then to get back to right coordinates, I have to multiply by alpha if I divide by alpha here. And that's a simply mathematical statement that approximately, when I am not looking very carefully, this neighborhood here looks like my original parabola. It is quartic function, but it looks like deformed parabola a little bit. And that's where we are. Now, amazing thing that happens next is you wash and repeat. That's called iteration. And you compute, this was relating R0 to R1, parameter for period 2. But then the same thing will work for R1 as a function of R2, where now I'm repeating period 2, sum of length 4. I keep getting a sequence of things numerically computable. You can compute them if you want to. If you write them as polynomials in x, in variable x, you'll go crazy. But if you just do it numerically, and now it happens that as n gets bigger and bigger, we already know from experiments, it means that there's smaller and smaller steps in values of n. That's controlled by the other Feigenbaum number delta. But we know that we can study what happens at R infinity. And you get an equation for a function which is a self-reproducing function. So it looks something like that. We'll change a name, and it depends on R infinity, so parameter doesn't change. So we'll drop the parameter, and instead of f, we call it g. And it says that there is a function that if you repeat the map twice, rescale what you call x, your distance in unit cube, by the number which turns out will be determined by this equation, you get a function that turns out cares only about one thing, that the maximum that you were blowing up, this guy here and here and here, that locally this maximum was quadratic. Now, it's possible to cook up examples where locally the maximum is something else. They're not natural, but mathematically you can do it. The only natural thing is that in a neighborhood or an extremal point, you pick up a quadratic correction because that's a local curvature. So now you have that in a limit as R0 converges to this infinite period 2 to the n period of the map, where n goes to infinity, you find that there is a solution to this. There is a function that just reproduces itself, and it doesn't care at all whether you're looking at chicken hearts or you're looking at, Rosler attractor Poincare section or whatever you were doing. This alpha is universal. It's just a pure number that you measure in all these experiments, and this function is a function that's unique, well-defined, etc. And how is it possible? Well, as we were doing these iterations, every time we made neighborhoods smaller, going, what I call my unit square, what my lenses blowing up, is very small. It's alpha to the n. Alpha is 2.5. So this is a big number as n goes away. So we are pushing everything that had to do with the original problem geometrically far away from a neighborhood where we compute this. We now have a situation that by construction, G at origin is 1, because that was this value of period, parameter value where you got the period 2. But if I put that in this equation, I get that alpha is G1.
Why is alpha 2.5?
Oh, why is it? We do not know. It's not 2.5. Let's see, I'm glad you asked that question. Well, we have it to about 1,000 digits, but alpha is in practice, I don't remember it, but it's 2.5091, tuck, 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 tuck. As I keep doing it, alpha goes to limit, which is not approximate, but exact. So that number is as universal as pi is universal. Everybody will get the same number. But we don't understand this number very well. We have it computed to thousands of digits, but we do not know whether it's transcendental or not. We have no proof that it's not some power of pi or some weird thing. As far as we can tell, this is a new number in the list of your, Euler numbers, Gamma Catalans, various numbers that appear in mathematics. And now we have been at it for, this is 1986. Very many field medalists even have been honing their teeth on it. Actually, there was a fields medal on this only 3 years ago. So the theory is more and more beautiful, mathematically more and more sophisticated, more and more incomprehensible. But we don't know. We do not know some basic things like, is this a transcendental number, algebraic number? We have every reason to believe it is, but it's very hard to prove such thing. We know that it exists. The solutions have been proven. This function exists. We know lots about its analytic structure. We know many things about it. But it's totally weird because it came from a very messy setting where you had simple models of things stretching and folding and looking approximate like parabolas, but not really meant to be. But by the time you renormalize everything to the border doesn't know what problem are you solving, because this neighborhood is so small that all the details in the Taylor series of your original one-dimensional function have been washed out. The only thing it cares about is that the first term is quadratic and let's say not quartic or something like that.
Would you get the same alpha if you say used like sine x and
yeah? So that's first thing that Feigenbaum did when he discovered this number.
Okay.
he had a nice programmable calculator that also had trigonometric functions, which is a big deal. So he ran it with trigonometric functions. And, other people have noticed that there is geometric convergence, but nobody realized that that's universal. That any function which is unimodal, meaning looks like a hump, and has a quadratic maximum will have the same universality class. That was the amazing thing that brought together, physics of the time, which was renormalization in quantum field theory and renormalization in condensed matter physics, with dynamical systems where nobody expected this at all. And it's a very beautiful function. If I was into tattoos, I might tattoo myself with this function. Other people have, I haven't told you about Mandelbrot sets, but you might have seen them in popular media. People have tattooed themselves with Mandelbrot sets, so this might be another candidate if you want to have a very sophisticated tattoo. And what is amazing about this is this piece of mathematics that just popped out 50 years ago and not. How simple can it be? Looking at nonlinear systems, and it says there is not a parabola, so it's not x squared, but there's a function. It's not exactly x squared. You have to iterate it. You have to have it eat itself. That describes a vast class of experimental situations, including the ones that Professor Fenton discussed in his lecture, and even includes, they're very happy that they found a period 3 window, but if you look at how period 3 window goes chaotic, it actually goes chaotic in this way. It's described by the same function. It goes to the period W. So it's a very common thing. And I will leave you with it. Profoundly unhappy that I haven't been able to produce some simpler, more penetrable argument to introduce it to this. So I will go and drink some tea or something. Hi, Anna.
Hello. How are you?
I have blue, professorial blues.
Around
It's a
the time of
beautiful
the
piece
day.
of thing, and I slaughtered it in front of your very own eyes. I'm ashamed. Okay, bye.
I had a question, if that's okay.